Okay, so section 8.2 focuses in on the Pythagorean theorem. Really practical use of right triangles. When you think of applications like in building or ramps, you can see right triangles everywhere you look. Okay, so the key here is going to be that we have these three sides, and we need to look at this longest side. The longest side always lives opposite that 90-degree angle. So if you find the 90-degree angle on the side that lives opposite it, we call that the hypotenuse. That's going to be key, because when we think about the Pythagorean theorem, we take that side and square it, and it's going to live by itself on the equation. Okay, it's the longest side. So what happens is it's always equal to the sum of the two smaller sides that we call the legs. Okay, so we see two examples here to start, and both of these examples use the Pythagorean theorem, except in one you're going to notice we're looking for a leg. The leg is unknown. Okay, in this one the hypotenuse is unknown, so they're going to feel a little bit different in terms of how we apply the Pythagorean theorem. When we're missing a leg, what ends up happening is we'll need to subtract to find that missing leg. And when we studied the distance formula earlier this year, I always used the Pythagorean theorem or applied it to that. So hopefully this feels a lot like review. If you adopted that philosophy to the distance formula to just turn it into Pythagorean theorem, this should be a pretty easy section for us. But when I'm looking for the leg, what happens is I end up taking the hypotenuse and I have to subtract the other leg squared. So if I'm looking at this and I know I want the leg, what I can do right away is just know that this is going to be 13 squared minus 12 squared. I mean, we can go through all the steps algebraically if we want, but if I know I'm looking for a leg, I know I'm subtracting, and that hypotenuse is the bigger side. He's got to be by himself. If I'm looking for the hypotenuse, I'm going to add. This is just going to be 20 squared plus 30 squared. Okay. Now, of course, when I do this, I now have the leg squared or the hypotenuse squared. So I am going to certainly have to take the square root of that. Okay, which is our very last step. Right. They don't really show that here, but if I took the square root of 25, that's how I get to 5. Okay, I'm going to do a couple of these with you, and then I'll let you practice some on your own. And if the answer is a radical and simplest form, I'll probably give you a multiple choice option. If it's a decimal, I'll just have you enter the decimal, rounded to 1 decimal place. So in the first one here, we're missing the hypotenuse, right? So what's going to happen here? We would have x squared, he gets to live by himself, he's the hypotenuse, equals 3 squared plus 3 squared. Okay? So what happens here, we still have x squared. This is 9 plus 9. So I have x squared equals 18. And what I want is x. So in order to find x, I would have to take the square root of both sides. Now this should look familiar to what we've been doing in our previous section. All right, we want to simplify that square root of 18 if we can. Is there a perfect square that lives inside of 18? And there is. That would be 9. So this is going to be x equals, let's chunk this up into the square root of 9 times the square root of 2. And then what we are left with is x equals 3 root 2. So it takes us back to what we were. Okay, so let's rewrite that 3 square root of 2. All right, now in the next one, a little bit different. What's missing is a leg. So again, what happens here is 15 is going to be by himself. He is the hypotenuse. So he's going to be equal to x squared plus 9 squared. So in order to find x squared, we'll have to subtract. So x squared is going to be equal to 15 squared minus 9 squared. If you want to jump to that right away, if you know I'm looking for a leg, I'm going to subtract the smaller from the larger, then go for it right away. Okay? So you're going to take 15 squared minus 9 squared. So I still have x squared. I haven't square rooted yet. This is 225 minus 81. When I subtract, I will get a perfect square. This is going to be 144. So that makes my life easy when I take the square root of 144 equals 12. Okay, so this triangle x would equal 12. That's what we're looking for there. Okay. All right. Now in the last one, some big numbers, so make sure you have your calculator handy here for this one. 65 is going to be by himself here. 65 squared equals x squared plus 25 squared. Okay, So now it's up to you whether you want to square those out or if you just want to plug them into your calculator. You know, if you have a calculator, like when we were in school, they're probably still hanging in our classroom. We don't have them. But if you have a calculator, you can just plug this in. 65 squared minus 25 squared. And then you move on with your life. That's fine. If not, if you have to go step by step, then that's how I'm going to walk you through this with the calculator. So when I square those, I get 4225 equals x squared plus 625. So now what I'm going to do next is subtract, right? I subtract 625 from both sides. So what I have here is 3600 equals x squared. And I just take the square root of that. So if x equals the square root of 3600, we have x equals 60. Okay, so the next example, we have some fractions. I know we're not crazy about those, but no need to panic. We can still apply Pythagorean theorem. We have x squared equals 4/9, and we're going to square the whole thing. Okay, 4/9 squared. Sorry about that, wrong sign. It's x squared plus 4/9 squared equals 5/9 squared. That's your hypotenuse that's going to live by itself over on that side. So not terribly complicated. I just square the numerators and denominators. So we have x squared plus 16 over 81. These should be familiar perfect squares to us. Equals 25 over 81. And since we have common denominators, that's not too difficult to subtract. We subtract 16 over 81 from this side and 16 over 81 from this side. So we have 25 minus 16. So x squared is going to equal 9 over 81. Okay. Which is 1/9. So we take the square root of both sides. And what I have is, when I take the square root of both sides here, x equals square root of 1 over square root of 9, which is just 1/3. Which is also the same as 3/9, 3/4/5, right triangle. Okay, I'm not going to give you any fractions the rest of the way. But what I'd like you to do now is give number 5 and number 6 a try on your own. And like I said, if they work out to decimals to one place, I'll have you enter your answer as a decimal. If not, we can do radicals in simplest form. I'll go multiple choice for that. So give those two a shot. Okay, so if we want to check our answers here, see how we did. Here you have x is the hypotenuse, so he's going to be by himself. So we're going to start off with x squared equals 16 squared plus 33 squared. So I get some bigger numbers here. So 16 squared is 256. 33 squared is 1089. That is 33. And then I have to add those together. So that's 1,345. And now I'm going to take the square root of both sides. So x equals the square root of 1345. So when I take the square root of 1345, I get 36.7. So I got 36.7 for that one. So for the next one, setup's a little bit different. 28's the hypotenuse, so he has to live by himself there. So we have 28 squared equals x squared plus 11 squared. Those are my two legs, x and 11. Okay? So we have to square 28. So 28 squared is 784. So next we would subtract 121 from both sides to solve for that x. And I have 663 equals x squared. And then we take the square root. So x is going to be square root of 663. Which is 25.7. Yeah, so I hope you got both of those.